And it looks like we're ready to go. All right. So, number 1. Yes. Oh man, we're off to a good start. So, which of the following does not describe a metal? So, you want to think about what metals do and what non-metals do. So, different things on here. So, the correct answer there is A, gain electrons, because we know our metals tend to be what? Cations or anions? Cations, which are positively charged, which means that they tend to lose electrons rather than gain electrons. So that's why A is the right answer. We look at the other ones. Do metals tend to form ionic compounds with non-metals? Yeah, they do. So that does describe. Are metals good conductors of heat? Yep, if you've ever put a piece of metal into a fire, you know pretty quick they conduct heat very well. Good conductor of electricity. Yep, that's why we make wires out of them. And are they found on the left side of the periodic table? Well, that's on this side, and that's definitely where we find all of our metals there. So that's why A is the right answer, and none of those other ones are the right answer. Questions on that one? Okay. How about number 2? Okay, so good with electron diagrams. Good. Number 3. Yes. Okay, so give the ground state electron configuration for iodine. And where's my periodic table? Here it is. So look at iodine here. Let's go ahead and write number 2 up there. Okay, so iodine's down here. It's in period 1, 2, 3, 4, 5. Okay, it's in period 5. And it looks like we have noble gas notation on the answers. And so for noble gas notation, we always look at the previous noble gas, which here is going to be krypton. Okay, so we write krypton. And then we track the periodic table the rest of the way through. So we're down here in period 5, so we've got 5s2 to get us through the first 2 of the S block. And then we've got to go all the way across the D block here. And remember, that goes as the period -1, so we're in period 5, so that's 4D. And we've got to go all the way across, so 4D10. Can't see that there, sorry. Okay, and so that takes us here to cadmium. And then we've got to come over to iodine, and so we're going to be at 5p, because remember the p block goes the same as the period. So 5p, 1, 2, 3, 4, 5. So 5p5 should be the answer there, and that comes out to be B. Okay, so we can use that periodic table to tell us exactly what that electron configuration is going to be. Any other questions on that one? Number 4. Yes. So, place the following elements in order of increasing atomic radius. We've got phosphorus, barium, and chlorine. And so we want to remember about atomic radius is how it increases or how it changes as we move across the periodic table. So it increases as we go down the periodic table, and it decreases as we go from left to right. Okay, so we need to look at the relative positions of these different elements here. So if we look at phosphorus and chlorine there, okay, we see that phosphorus and chlorine are in the same period, so there's no change up and down. However, since phosphorus is to the left of chlorine, it means it's going to be bigger than chlorine. So we know that phosphorus is bigger than chlorine, looking at those two. Okay, and then we want to compare phosphorus and barium. I'll need to zoom out here to get all of those in there. And so we've got barium down here and phosphorus up here. Well, barium is much farther down than phosphorus is, so barium is going to be much bigger than phosphorus. And so we know that barium is bigger than phosphorus. Now, what was the problem asking for? It says in order of increasing atomic radius, so I have these backwards. So we have increasing, so chlorine, and then phosphorus, and then barium. And that would be B. Okay, so we look on that left to right, how we are, and then up and down. Okay. Questions on that one at all? There's one page. Okay, number 5. Yeah, okay, I figured if atomic radius got hit, ionization energy was going to be there as well. See, that was number 4, wasn't it? I put number 3. That was 4. Okay, so number 5, increasing ionization energy. So we have potassium, calcium, and rubidium. So remember, ionization energy has just the opposite trend of atomic radius. So it decreases as you go down the periodic table and increases as you go from left to right. Okay, so let's compare some of these. So if we compare those first two, potassium and calcium right here, so they're in the same period. We see potassium is to the left of calcium, which means that potassium is going to be less than calcium because it increases as you go from left to right. So we know that potassium is less than calcium. And then we need to compare rubidium, which is right below here. And so since we're down below that, that's going to be lower than potassium, which means it's going to go over here like that. So rubidium is less than potassium, which is less than calcium, and it wants an increasing order, and that's how we have it. And so that order is going to be E for number 5. We do have some seats down here if you guys want to sit and scattered seats all over the place. That floor gets pretty hard after an hour. All right. Number 6. Is that you? Okay. Got to speak up a little bit. So number 6, the tricky part with number 6 is that it is an ion. We're looking for selenium 2-. And so the way that I like to do this first is just to do the element and then apply the charge. So if we look at the element selenium, we see it's here, it's number 34. Okay, so we can again go across the periodic table. It's going to end in 4p4, okay, for selenium, the atom, okay, because it's the 4th element in the p block in the 4th period. Okay, so we don't need to write everything out because they use noble gas notation. So the previous noble gas is argon. So it's going to be argon. And then we track as we go across. We have 4s2 to get us to calcium, 3d10 to get us to zinc, and then 4p4 to get us to selenium. Okay, so that's selenium, but now I have a 2- charge. So what am I doing to that configuration? Adding 2 electrons, and where are they going to go? Well, they're going to go on that highest level there. And so we're going to add here, so not 4p4, but 4p6. Oop, not 2 electrons, 2-. Okay, so we have argon, 4s2, 3d10, 4p6, and that answer would be D. Okay, so that would be D. So you got to make sure that you're not just doing the atom, that you're doing the ion, or just asking for an ion. Nice turnout, by the way, for you guys coming out in the evening. Questions on that one? We do have some seats down in the front if you just came in. So I've got a couple down here, a couple over here. Let's see, number 7. Yeah, I knew 7 was coming up. I should probably just plan on doing most of these. Okay, so with number 7, there's no way just to look at these and know if they're diamagnetic or paramagnetic. You're going to have to do the electron configurations of the valence shell. Okay, so that's going to tell you if it's diamagnetic or paramagnetic. So we'll just do the elements here. We've got fluorine, we've got zinc, we've got lithium, we've got vanadium, and we've got rubidium. Okay, so for fluorine, so for the valence shell here, it's going to be 2s2, 2p5. Okay, so we're going to want to do an orbital diagram. So we've got our s and then our p's. And so 2s2, 2p5. And we notice that we have an unpaired electron there, and that means it's what? Paramagnetic. Unpaired means paramagnetic. And it's looking for diamagnetic, so fluorine's not the answer. If we look at zinc, zinc goes through the 4s2s and then 3d10. So zinc has a 4s2, and then there's 5 d orbitals there. So 4s2 there, and then 3d10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So for zinc, we see that all of our electrons are paired, and so that means that zinc is diamagnetic. Good. So that's why B is the answer. If we look at the other ones, we see lithium there in group 1A. That just has a 2s1. So that's just going to look like that. Vanadium is going to be 4s2, 3d3. So it's going to be here, and then we've got 5 d orbitals there to fill in. So we're going to have 4s2, and then 3d3. We see vanadium is really paramagnetic. It's got 3 unpaired electrons there. And then rubidium is also a group 1A, and so that's just going to be the 5s1, and so that is also going to be paramagnetic. Okay, so the only one that has all the electrons paired there is zinc. Okay, that problem takes a long time because you've got to look at each and every one. Questions on that one? Yes?
Can we just tell because zinc has an even number of electrons?
No.
No, we have to do that.
Oxygen has an even number of electrons also, and it is paramagnetic.
Okay.
Yeah. You can tell if it has an odd number, because an odd number can't have everything paired. But an even number may or may not be paramagnetic.
Okay.
Yeah. All right. I don't know if you could have applied that on this one. You may have been able to. Yeah, I think everything was odd except for that one, so you probably could have done that here. You got to be careful. All right, number 8. Yes. So give the name for SNO. Snow. It's just snow. That's all it is. In ad speak, by the way. All right, so we have SNO there. So tin is it's one of those funny elements because it's not a transition metal. It's just outside the transition metals. However, it does have more than one charge. The two elements we really need to worry about that with are tin and lead. Those are two of the most common metals that are outside of the transition metals, but they do have more than one charge. So this one may have got you a little bit on that one. But they didn't give any options without it. So what we do here is we've got to figure out what's the charge on tin here. And so we see oxygen. Oxygen's a group 6. So that's going to have a -2 charge in an ionic compound, metal and non-metal. There's only one oxygen, so there's a total of 2 minuses. So I always put the individual atom charge up top and the total of those atoms down below. So there's just one, so -2. And that has to add up to 0. So what does my total from the tin have to be? It's got to be +2. And there's only one tin to have those +2. So tin must be plus 2, which means that this is going to be tin 2 oxide. Okay, because that tin has a plus 2 charge to counteract the oxygen's minus 2. So that would be B, tin 2 oxide. Let's see, number 9. Yes. So we want the chemical formula for sodium perchlorate. So we look at our polyatomic table here, and we see perchlorate here is a ClO4 with a minus charge. And this is the exact one that you're going to get on your exam, except for you're not going to have these bond angles on there. Okay, but you'll have that polyatomic table, you'll have the electronegativity table, and then most of that. Okay, so perchlorate is ClO4 minus, and we're looking for sodium. Now sodium is in group 1, which means it's going to form a plus 1 charge. So we've got a plus 1, we've got a minus 1. We look at the lowest common multiple, that's 1. And so we're just going to have one of each. And so it's just going to be NaClO4. Questions on that? Right. Number 10. Feeling pretty good at the non-metals there? Good. Number 11. Yes. Okay. Calculate the molar mass for MgClO4 which is magnesium perchlorate. Okay. So we've got MgClO4, and there's 2 of those. Okay. So when we look at this, what we have is we have 1 magnesium ion, and then we've got 2 perchlorate ions. And so what we really want to do is calculate the mass of the magnesium, or not calculate it, but find it. And we see that that's 24.31 plus, and I'm going to find the mass of the perchlorate. I'm going to multiply that by 2 because I've got 2 of them. And chlorine is 35.45 plus 4 oxygens, each at 16. Okay? And so I take that 4 times 16, add that to 35.45, multiply that by 2, and then add the 24.31, and you should get 223.21, and of course that has units of grams per mole. Questions at all now? Okay, good. Number 12. Yeah. I have a feeling these next few are going to be calculated out here. So for number 12, we want to calculate the mass percent composition of lithium in Li3PO4. So all we want to do here is just say, let's say that we had a mole of this material. And we want to say, okay, if I had a mole of this material, what would the mass of lithium be in that material? And then what would the mass of the mole of that material be? Okay, and then multiply that by 100, and I'll get my percent. Okay, so for the lithium, hope I added that one up right. I did, yep. Okay, so for lithium, I've got 3 times 6.94. Okay, because for every mole of Li3PO4, let me write out the formula here. For every mole of Li3PO4, I'm going to have 3 moles of lithium there. Okay, so 3 times the molar mass of lithium is going to give me how much lithium I have. And now I just need to find the molar mass of all of it. So that's going to be 3 times 6.94 plus the mass of my phosphorus, which is 30.97, plus, and I've got 4 oxygens, so it's going to be 4 times 16. Okay, so when I add all that up and multiply by 100%, I get 17.2 Okay, so just taking the mass of the element we're looking for divided by the mass of the entire compound, the molar mass of the entire compound. Questions at all on that one? In that case, we'll just turn the page. Number 13. Thought so. So this one's a little bit harder. We didn't look at a lot of this in class. So look for the empirical formula. We did talk about that. Of a compound that is 64.8% carbon, 13.6% hydrogen, and 21.6% oxygen by mass. So when it says a percent, that means I've got and by mass, that means that's how much weight I have, percent. So if I just make an assumption that I have a 100-gram sample, well, that tells me how many grams of each of these elements I have. So if I assume a 100-gram sample, I'll go ahead and write that out. So then what I have is I have 64.8 grams of carbon. I'm going to have 13.6 grams of hydrogen and 21.6 grams of oxygen. Once I have the number of grams of each of those, I can find the number of moles. So we're going to say times 1 mole per 12 grams times 1 mole per 1 gram and times 1 mole per 16 grams. So we end up with 5.396 moles and 13.6 moles of hydrogen and 1.35 moles of oxygen. Okay, so now I have kind of a chemical formula here. I can write that I have C 5.396, H 13.6, O 1.35. And once I get to that point, I want to get everything to a whole number, so I'm going to divide each of those by the smallest number in there. So the smallest is 1.35. So I'm going to divide everything by 1.35. And when I do that, I get C 4, H essentially 10, and O just 1. Okay? We can write the 1 if we want because they did in the answer. And so that's my empirical formula. And so that's why the correct answer there is A. C4, H10, O1. Okay, so we're just going to take that percent, turn it into grams by assuming a 100-gram sample, take the grams, turn it into moles, and then get those moles to whole numbers. And that will give us our empirical formula. Okay, questions on that one? Yeah.
So just with that really quick, you can divide and then you're just going to round up or round down?
Well, I didn't. After the division?
Yeah.
Yeah, so if it's really close, because I know that H probably comes out to like 10.01. Yeah, that's within an experimental error. The only ones you wouldn't round is like you're going to get like these whole fractional numbers, like 0.25, 0.33, 0.5. Those you would not want to round. But if you're getting like 0.01 and 0.02, those are okay to round. So. All right, number 14. Okay, so number 14, how many moles of pyridine are in 3.13 grams of pyridine? Okay, so first thing we're going to need to figure out is what is our molar mass of pyridine? We have the chemical formula. We've got to figure out the molar mass because that's my conversion factor between mass and moles. So for pyridine, C5H5N, we can take 5 times 12 for my carbon plus 5 times 1, my hydrogen, plus 1 times 14 for my nitrogen. And if you want, you can include the decimals that are on the periodic table. I'm just keeping my math simple here. Okay? And so we're going to get, 79 grams per 1 mole. Okay, so now I know the molar mass, 79 grams per mole. I have 3.13 grams, and so I want to take my value, 3.13 grams. I'm going to multiply it by my conversion factor. Now remember, a conversion factor can always be written 2 ways. I can say 79 grams per mole or 1 mole per 79 grams. Any conversion factor can be flipped up and down. Okay, 12 eggs per 1 dozen per 12 eggs. Same idea. So which conversion factor do I want, first or second? I want my second to put moles on top. That'll allow my grams to cancel. My grams cancel out there. And when I do that, I get 0.0396 moles. And that would be choice D. Questions at all on that one? Pretty good? All right. 15. Yeah. I knew 15 was coming. So 15 takes 13 a step farther. Okay, so here's a case where we know the percent makeup by element, and we're given a molar mass of the compound. So we can find the empirical formula, and then using the molar mass, we can figure out how many multiples of the empirical formula get us to the molecular formula. Okay, so we're going to do the same thing. We're going to assume a 100 gram sample. And so we're going to have 40.0 grams of carbon. We're going to have 6.71 grams of hydrogen, and we're going to have 53.29 grams of oxygen. We're going to convert each of those into moles, so times 1 mole per 12 grams, 1 mole per 1 gram, and 1 mole per 16 grams. Okay, when we carry this one out, we get what? I've got to try to read my writing here. We get 3.33 moles. We get 6.66 moles. I guess 6.71. I had actually carried out an extra decimal there before. And then we get 3.33 moles here as well. Okay, so we have an empirical formula initially, our weird one, of C.33, H 6.71, O 3.33. We're going to divide that by 3.33, divide by 3.33, divide by 3.33, and we get C, H, and that's going to round to 2, and then just O. So that's my empirical formula there. Okay, now, when we look at this, we see that this has a molar mass, this empirical formula have a molar mass of 12 plus 2 times 1 plus 16, which is equal to about 30 grams per mole. Now, when I look at the problem, it says the molecular weight of the molar mass has a value of 60.05. Okay, so how many of those empirical units do I need to get to 60? I need 2 of them. Okay, it's always going to be an exact multiple of it. So I need 2 of those, and so that means my formula would be C2H4O2. So that would be my molecular formula for that. Okay, so that CH2O, that's my empirical formula. That's like the basic building block of this chemical. Right? And so each one of those building blocks weighs 30. So my only possibilities for molar mass would be 30, 60, 90, 120. The molar mass was given in the problem at 60, and that means I have two of those building blocks. And so that means it's got to have 2 carbons, 4 hydrogens, and 2 oxygens. All right. I know we didn't go over that in class. It wasn't in the reading. I don't think we have any of those on the exam. But it's good to know how to do it. All right. Number 16. Yes. So 16 trips some people up just in the wording. Sorry, time for a throat drop. Okay, so 16 says there are blank paired and blank unpaired electrons in the Lewis symbol for a phosphorus atom. So if we look at a phosphorus atom, we see it's P, and it's in group 5, which means it has 5 valence electrons. So we're going to go 1, 2, 3, 4, and then that 5th one is doubled up. Okay? And so when we look how many electrons are paired, there's 2 paired, not 1 pair, but 2 electrons paired. It's an important distinction. And 3 unpaired electrons there. So the answer is E. Okay, it's E. Questions on that one at all? Okay, number 17. Okay, good. Number 18. We did that one enough times in class, I think. Number 19. Yes? So, of the ions below, only blank has a noble gas electron configuration. We can do this one probably easiest looking at the periodic table. So let's look at each one of these individually. So iodine. So it says iodine plus. If it does iodine plus, what do I do with its electrons? I subtract one so it goes from 53 to 52. That's not a noble gas. Okay. Sulfur 3 minus. Okay, sulfur's up here. And so if I did 3 minus, what does it mean I did? I added 3 electrons. It has 16. If I added 3, it's going to have 19. Potassium is not a noble gas. P5 minus. Phosphorus is here. 15. We go 5 minus. It means we added 5 electrons. 1, 2, 3, 4, 5 with 20. Calcium is not a noble gas. Okay, and P3 plus. So phosphorus here, if I go 3 plus, I start with 15. I take 3 away. It means it would look like it has 12. It means it would look like magnesium. Magnesium's not a noble gas. And then, I skipped one, didn't I? I skipped the answer, which is phosphorus 3 minus. So phosphorus here. Am I on the wrong? No, I'm on the right problem. No, I'm not. Which one am I doing? Oh, 19. Okay, I started looking at 17. I'm sorry. You guys got to correct me faster than that. My brain's not that fast. So you're probably going, which one is he on? So C is chlorine minus. That's the correct answer. So chlorine normally has 17, and then we add 1 for a minus, and so now it has 18, and it looks like argon, and that is a noble gas configuration. So that's why chlorine's right. If we look at oxygen 2 plus, that would look like carbon, and K minus would look like calcium. Got to remember to see when you see that minus, you add electrons, you see the plus, you subtract electrons. I know it's weird like that. Let's see. Number 20. So 20, very much similar to that. It wants to know which of the following does not have 8 valence electrons. So if we look at A, bromine, bromine's in group 7, so that means it has 7 valence. Bromine minus means it added 1, that's going to give it 8. Calcium is in group 2, so it has 2 valence electrons. If it's calcium plus, I removed 1, that means it has 1 valence electron. And so that's why calcium plus is the right answer. It does not have 8. If you look at rubidium, it normally has 1. We take that 1 away, and then this becomes its valence shell up here, and so that becomes 8. Xenon is a noble gas, so that has 8. And then E isn't right because of calcium there. Let's see, 21. Okay, so for a given arrangement of ions, the lattice energy increases as the ionic radius does blank, and as the ionic charge blanks. Okay, so for 21, or for the first one, for the ionic radius, so as your ionic radius goes down, that means that the plus and minus charges are able to get closer and closer. And what happens to charges as they get closer? They attract more. Okay, so that releases more energy. And then, as the ionic charge does what? As it increases, that attraction gets greater because of a higher charge. And so both of those two things promotes an increase in lattice energy, because that's an energy release when the ions come together from a gaseous form into a solid. So when radius decreases, they're able to get closer, more attraction, releases more energy, and as charge goes up, it's a greater attraction, releases more energy.
What specifically is the lattice?
What's a lattice?
Yeah.
That's that three-dimensional arrangement of ions in the solid. Yeah. Just like a lattice you put up in your garden, that's a two-dimensional lattice. Ionic solids have a three-dimensional lattice. All right. Next page. Number 22. Okay. So probably the easiest way to do number 22, I'll go ahead and write this one out, is to see how many electrons you would expect with argon 3d4, and then see which of these has that many electrons. So if we look at argon 3d4, okay, well, argon has 18, and then 4 electrons here, it's going to be 22 electrons. So if we look at vanadium 3 plus, vanadium normally has 23 electrons, and if it's a 3 plus, it means it's going to have 20 electrons. If we look at K plus, potassium normally has 19 electrons, and if it's a plus, it means we removed one, so that means it's got 18 electrons. Chromium 2 plus is the answer. So chromium normally has 24 electrons. If it's a 2 plus, it has 22 electrons. So that's why that's the answer. Manganese 2 plus. So manganese has 25, and if it's a 2 plus, that means it's going to have 23 electrons. And iron 3 plus. So iron normally has 26, but as a 3 plus, it's going to have 23. Okay, so the only one that matches the proper number of electrons is going to be that chromium 2 plus. Questions on that one? Yeah.
Why would you say 4
So this indicates that it's lost those 2 electrons. So you definitely have a 2 plus ion, at least a 2 plus ion. It's possible you also lost the D electron in there as well. So, but there's no way to know. Yeah. So if it had given you like chromium 2 plus or manganese 3 plus, there's no way to know which of those would be correct. Yep. They both be correct. All right. 23. Its definition, covalent bonds are mostly non-metal. 24. Good. 25. Yeah? So this is a lot easier when you have the table, which you'll have, because that's your strength and electronegativities, and fluorine has the highest number, so it's the most electronegative. Yeah. It's kind of a silly question in retrospect to put on here, knowing I give you guys the table. Because that's all you have to do is to look up their values on the table you're given on the test, and you'd be able to get that one. So, but fluorine's the most electronegative, not only of that list, but of the entire periodic table. 26, same thing. Just look up the values. If you didn't have the table, what you would say is, so electronegativity increases as you go up and to the right, and it decreases as you go down and to the left. Okay, but you have the table, so you don't need to worry about that. Let's see, number 27. Yes, so the ion ICl4 minus has blank valence electrons. And I know that the font on here is kind of weird, and it's hard to see that that's a Cl, but it is. Okay, so ICl4 minus. So iodine is in group 7, so it has 7 valence electrons. Chlorine is also in group 7, so it has 7 valence electrons. I've got that minus charge there, and so I've got to add 1. So I have 7 plus 28 is 35 plus 1 is equal to 36 electrons there. So the answer is E. Pretty good at that one? Got to make sure you count valence electrons or you won't be able to do dot structure. Let's see, 28. Yeah? Okay, so 28, Lewis structure of AsH3 shows X number of non-bonding electron pairs on the arsenic. Okay, so we look up arsenic there. We see that it's a group 5, which means it has 5 valence electrons. Hydrogen has 1, and there's 3 of them. And so we have 8 valence electrons. We put arsenic in the middle, attach the hydrogens to it. That used 6 electrons. I have 2 left. Those have to go right there on the arsenic. I've got no electrons left. The question says, how many non-bonding electron pairs? And I've got 1 pair of non-bonding electrons on the arsenic.
So when you live in Lewis structures, you release element, normally doesn't say that.
Or the one that's listed first. Okay, or the first non-hydrogen. Because you can't put hydrogen in the middle. Okay? Do you normally have my class? Oh, so you didn't hear about the one-armed kid playing Red Rover. Yeah, you can't put the one-armed kid playing Red Rover in the middle of the thing. So I know it's terrible, isn't it? I'm sorry. If you didn't hear that, yeah. Hydrogen's the one-armed kid. Once it forms the one bond, it's done. Hydrogen can never go in the middle. Yeah, I know you're going to remember that the rest of your life. I'm sorry. That's just the worst analogy ever, but it works. All right. Let's see where we're at. 29. So in which Lewis structure does the central atom have a non-zero formal charge? And this is another one of those problems where you've got to work each one of these out. Okay? And so if we do that, okay, so if we look at PCl3, I'm not going to go through all the details of the dot structures. CH2Cl2. It doesn't really matter where I put these bonds here. HCN. C2H4. Oh, that's a weird one. We wouldn't give you anything quite that weird for the C2H4 NH3. Okay, so we're going to split all of the bonds. Got to put on the lone pairs on these guys. Yeah, this problem would take a really long time during the test. The potential for an error is high. We try not to do any of these kind of problems on tests, but every once in a while they sneak in there. Alright, so remember to do formal charge. We take the number of electrons an element normally has minus the number it's been assigned in the atom. We're just looking for that central atom. So we don't need to do all of them for formal charge, just that central atom. Okay, so phosphorus normally has how many electrons? It's in group 5. So it normally has 5. Okay, and how many did we assign it here? 1, 2, 3, 4, 5. So 5 minus 5 is 0. It has a 0 formal charge. It's good to go. Carbon here, carbon normally has how many? 4. How many did we assign it here? 1, 2, 3, 4. So 4 minus 4, 0. We're good. Carbon here, same thing, normally has 4. Here we've assigned it 1, 2, 3, 4. So 4 minus 4 is 0. The carbon here is 0. Both of these carbons you can consider 0. They're like those interior atoms we talked about today. And so each of them have 1, 2, 3, 4, 1, 2, 3, 4, just like those other carbons. So they both have formal charges of 0. Nitrogen normally has how many? 5. And here it's given 1, 2, 3, 4, 5. So it also has a 5 minus 5, 0 formal charge. So all of our central atoms here have a formal charge of 0. It says which of them have a non-zero formal charge. Well, that's none of them. They're all 0. So the answer is E. Questions on that one? I know you're always suspect of those ones that are like none of the above or all the above. For good reason. Number 30. Yes, so another formal charge question. Is formal charge just really confusing to you guys? Okay. So I'll talk through the steps on this one in a little more detail. Okay, so we have a nitrate ion here. It has a negative charge. That's not terribly important. It's important when we finish our formal charge to make sure we've assigned all of our formal charges correctly, because they all have to add up to the overall charge on that ion. So we're just looking for the formal charge on nitrogen, but we'll go ahead and do all of them here. So to do formal charge, first thing you've got to do is you do a valid dot diagram. Here we were given a dot diagram, so we didn't have to worry about that. The next step that we do is we take all of the bonds in the molecule and we split them. We split the electrons in that bond. So for each bond, one goes to one atom, one goes to the other atom. If it's a double bond, 2 go to one atom and 2 go to the other atom. Okay, so that's why I make those little squiggly lines here. So I'm just splitting the bonds to tell us that one goes to one atom and one goes to another. Okay, so if we go to this oxygen here, so our formal charge is always going to be equal to the number of valence electrons that atom normally has minus the number of electrons we've assigned it in that molecule. Okay, so oxygen normally has how many? 5? Wrong. 6? I said wrong to me because I was like, yeah, it has 5. No, it does not have 5. That was my wrong, not your wrong. So it normally has 6. How many does it have here? It's got 7. I've got 3 lone pairs. Those are 6. And then it's got the 1 electron from that bond. So 7. So that oxygen has a formal charge of -1. If we look at this oxygen here, well, that is the exact same arrangement, 3 lone pairs and half a bond. That is also going to be 6 minus 7. So that's equal to -1. If we look at this oxygen here, okay, oxygen still normally has 6. How many is it assigned here? It's 6. It has 2 lone pairs for 4, and then 1 electron from each of those half bonds there. So that's another 2, so a total of 6. So the oxygen there has a formal charge of 0. And then for the nitrogen, formal charge. So nitrogen normally has how many? 5. It's group 5. How many have we assigned it here? We've assigned it 4. We've split 4 bonds up and it has no lone pairs. So 5 minus 4, well, that's equal to a +1. So we've got a +1 on the nitrogen, a -1 on 2 of the oxygens, and a 0 on the other oxygen. So -1, and +1 add up to -1, which they should because that's the charge on that particular ion. Okay, so the question asks what's the formal charge on the nitrogen, and so it's a +1. So it's A. Does that help? Feel a little better? Okay. I'm sorry, I went through that other one really fast, and you're probably going, what the heck is he doing? You guys ever watch Jeff Dunham? Yeah, he probably felt like Peanut. I love Peanut. All right. I didn't mean to go that fast on those. So, number 31. Yes. Okay. Okay, so for 31, we're doing SO3. And I'm just going to take you to a point where you've got to decide what to do with the dot structure. So if you were doing your dot structure of SO3, you would get to this point where you've assigned all of your electrons, but you haven't satisfied the octet of the sulfur. Okay, so what are our options? Well, we could bring a pair of electrons from this oxygen down and form a double bond there, or we could have brought a pair from this oxygen and formed a double bond there, or we could have taken a pair from that oxygen and formed a double bond there. Each of those would be equivalent resonance structures because you would have 2 single bonded oxygens and a double bonded oxygen. And so that gives me the possibility of 3 equivalent resonance structures. And that's all it is. There's no way just to look at the molecule and say it's going to have this many resonance structures. You've got to do the dot structures, and you've got to make sure you do the dot structure right, and then say, how many different ways can I satisfy the octet? Okay, how many different ways can I form a multiple bond? Because that's when you're going to get resonance, when you have to form a multiple bond. Okay, how many ways can I form multiple bonds on this structure? And that's going to be the number of resonance structures. Questions on that one? Okay, let's see, 32. Okay, pond angle in NH3 is, okay, so if we look at, the dot structure for NH3, you're going to get that. I'm not going to go through doing the dot structure. I'm hoping you can do that. So we look at that dot structure and we see that we have 4 electron pairs. 3 are bonding, 1 is non-bonding. Okay, so we see 4 electron groups, 3 bonding, 1 non-bonding. So electron geometry is tetrahedral. That's not what it asked for. The molecular geometry is trigonal pyramid. It didn't ask for that either. This just has the bond angles at less than 109.5, and this is why we left this off, because this is just confusing. And so remember we said before today, if you have a regular tetrahedron, your approximate bond angle is about 109.5, and each lone pair that you have pushes the bond angles in about 2 degrees. So we go from about 109.5 in about 2 degrees, and we're going to be right around 107 degrees. Okay, so that's why the answer there is B. You just have that one lone pair. It spreads out a little bit, takes up a little more room in the bonding pairs, and pushes those bonding pairs in a little bit. Everybody good with that one? Yeah. No angle numbers, yeah. Just because they're a little misleading. So, all right. Number 33. No? 34. You want to see 34? Okay, we'll do 34 real quick. So, xenon tetrafluoride. So the first thing we need to do is a dot structure. And it's weird with the xenon, it's got 8 valence electrons. Fluorine each has 7, so you got 28 from that. So you got a total of 36 electrons. So you put the xenon in the middle. Attach the fluorines to it. And that used up 8. I've got 28 left. I fill my octets on my fluorine. There we go. So that used 6 on each of those. So that used a total of 24. I have 4 left. So those other 2 pairs are going to go on the xenon there. So I have 6 electron groups, 4 bonding, 2 lone pairs. Oops, that's the wrong sheet. No, there it is. Okay, so 6 electron groups. I've got 4 bonding with 2 lone pairs. So I have an octahedral electron group geometry and a square planar molecular geometry. Okay, so the answer there would be C. All right, questions on that? All right, right at an hour. That's all it should take you tomorrow, right? Okay, well, good luck tomorrow. Last year the average was right around 80, so hopefully you guys will beat that. Good luck.